is a valid tree. So in this example, it is a valid tree. And if we take a look at this example, this is not a valid tree because there is a cycle in here. And there could be cases where these are not connected, so those are going to be not valid tree. So in order to be a valid tree, as you can see, for number of vertices, there is a n-1 number of edges. So first thing first, we can take care of this case really quick. So n-1, which is the vertices number. If it's not equal to the edges number, then we can return false right away. Okay, now the next goal is to traverse every single of them and see if they are connected. So if they are connected, and then we can say if they are connected, and then we can say this is just true. If they are not connected, then this is false. This is not a valid tree. So we could do traversals, BFS, DFS. It doesn't really matter. So let's do DFS in this case. So first thing first, let's create our adjacency list. I will be using map for that. So this is going to be our graph. And for edges, I will be using this edge values and then transferring into our graph. So what we can do is graph compute if absent and add a to it, and for value I can create new array list and add b into it. Thing goes to from b to a. So for given edge, we created a graph, and then it's like this is a, this is b, so we'll be adding a to 1, and then it's like next time when we see a to 2. So this list will be growing, and this is a bidirectional, so we're doing the same thing for b as well. So now we need to have a way to track if we have seen these nodes. So we can create a set for that. Visited hash set, and what we can do is we'll call our DFS in here, and we'll come back for the parameters, and we will return visited size if it's equal to the vertices number. So if they are, that means we have visited everything. And then that means also they are connected. If not, it means there is a disconnection between somewhere, and it's not a valid tree. So what we are going to pass in here, we are going to pass our graph, we are going to pass our visited, and also we need to pass our starting point. So let's create a dummy, not dummy, it's just like the starting point, which is initiated to 0 with a new array. So cool thing about this compute if absent, so in case if all those edges, like in this case, if we happen to have 0 in here, we will not override it. So because like there is a list of 1, 2, 3, and 3 in here already, and when we are saying 0, create this new array list, it will actually not override it. So just in case if it's absent, we will do it. So in this case, it's not absent, so we're good to go. Okay, we're passing this 0. Okay, now create our DFS, and in here I'm passing our graph, passing our set, and also our node. Okay, so first thing first, let's check if in visited it contains given node. If it does, then just return it. Now we can say visited node, because like we are processing this one, and for int next node, which is coming from our graph, getting it this node. So this is the neighbors. Basically, yeah, we can say neighbor or next node. That's a neighbor, and we will be calling our GFS on it. So graph is going in here, visited is coming here, and our neighbor. So, yeah, so this is about it. Let's real quick for time complexity. This is since edges and vertices are equals, usually for graph it's O A E plus V, which means edges plus its vertices, but in this case, since they are just very similar to each other, by -1 we can say time complexity is O of n. We can just combine them, and same thing goes for space complexity. We created a graph in here extra. We have extra space for visited, so same thing, it's O of n, since edges and vertices are, there's not much of difference.